Wait for a few seconds. Okay, let's get started. Hey, look, welcome everyone to the 9th CAT for Assurance virtual panel. The topic of the panel is hardware IP security in the age of heterogeneous integration. I cannot think of any more timely topic than this. I think all of you are aware about the rise of heterogeneous integration, the 3D chiplet-based designs, things like that, and IP security has become such an important problem in the context of that technological progress. So we'll talk about that. We have a truly distinguished panel here to shed light on this topic. As you know, this is about 1.5 hour panel. I will introduce the moderators to you. But before that, I will talk about the CAT for Assurance Initiative briefly. I'm Shahrukh Vunia from University of Florida. CAT for Assurance Initiative was launched October 2020 during the peak of pandemic by members of the hardware security community. Quite a few members came together and wanted to come up with a web portal and associated activities, including webinars, so that we can disseminate hardware security research activities to the broader community in a timely manner. If you go to the website, you'll see about 56 CAD tools total on broad topics of hardware assurance. As you know, assurance is a much bigger topic than security. It does encompass security as a major focus, but it includes reliability, it includes trust and other aspects of assurance. We have over 3,000 benchmarks in the website. If you are interested to use them for your research, please feel free to do that. More than 80 contributors. About 3,000 users, 40,000 page views. This data is a little bit dated because you didn't get the latest one from Google right in time for this panel. So definitely the numbers have increased quite a bit. We have done 17 tool demos / webinars for the last 3 years and 8 virtual panels. This is the 9th one, as I mentioned before. In these webinars and panels, we have more than 2,000 registrants and more than 1,500 attendees. So definitely, given the size of the hardware security community, definitely these numbers are very, very impressive. And this effort is being led by myself, Professor Gang Ku, Professor Sung Yi Ho, and Professor Ye Jin. I would like to invite all of you to participate in the CAT for Assurance initiative. You can use the tools benchmarks in the website. You can upload your tools benchmarks. There's a link to upload. If you want to do that, please let us know. And you can also give tool webinars to the broader community. And finally, you're also welcome to organize or participate in these virtual panels. We would like to acknowledge our sponsors, IEEE CEDA, that's IEEE Council on Electronic Design Automation, and a new committee called HSTTC, that's IEEE Hardware Security and Trust Technical Committee, that is an umbrella within IEEE CEDA activity, and also Warren Benham's Institute at UF, Mercury, Northrop Grumman, and Huntington Ingalls Industries are also our technical sponsors. A little bit about the HSTTC, that's the Hardware Security and Trust Technical Committee, led by Professor Gang Ku and Professor Ye Jin. As I mentioned, this is an initiative inside IEEE CEDA with the goal to increase the global awareness of hardware security and trust through organized events. And this particular panel is one activity sponsored by HSTTC. Just wanted to mention that. Just to let you know that the previous webinars are recorded and available. If you have missed it, available in the IEEE CEDA website. And this is just a listing. You can see here we have a lot of webinars, a lot of panels. All the video recordings are available there if you would like to access that. Now, coming to today's panel, as I mentioned, we have a truly distinguished panel here, and together they pretty much encompass all aspects of hardware security and trust I can think of. We have two rising stars, moderators, Rojin Iasei and Banafe Sebar Latibari from University of Arizona. Very pleased to have them as moderators. And we have Professor Farina Kushanfar from University of California, San Diego, Professor Todd Austin, University of Michigan, Professor Ahmad Reza Sadeghi from TU Darmstadt, Professor Saoyan Yu, also an NSA program director, and Professor John Oakley, Semiconductor Research Corporation, and Shanda Koteshwara from IBM Research. So that would be the formation of our panel. With that, I would quickly introduce the two moderators, and then the moderators would take over the panel. Dr. Rosin Iasi is an assistant professor at the College of Applied Science and Technology, University of Arizona. She earned her bachelor's degree in electrical engineering from Surrey University of Technology, a master's and PhD degree at University of California, Irvine, where her groundbreaking research introduced graph neural networks as a powerful new model for integrated circuits and its transformative potential in hardware security. Her current research focuses on the innovative application of machine learning and AI to cross-layer security, with an emphasis on hardware and cyber physical systems. We also have Banafse. Banafse is a postdoctoral researcher in the Electrical and Computer Engineering Department at the University of Arizona, affiliated with the Center of Semiconductor Manufacturing, or CSM. She received her PhD from the University of California, Davis in Electrical and Computer Engineering. Her research focuses on applying machine learning to hardware design and security, as well as transformer model optimization. Currently, she is collaborating on the AI HDL League at the University of Arizona, a competition that explores the use of GPT for hardware design and security solutions. Again, we are very pleased to have Rosina and Banafse to moderate this panel. Just a couple of quick announcements. The panel will be recorded and available for whoever has missed the panel. And if you want to check back, you can absolutely look at the recording. And finally, for question and answer, use the Zoom Q&A feature. You know how to use that, but use that feature, write your question. You don't have to wait until the end of the panel. You can write questions anytime. With that, I'll hand over to Rosin and Banafse to moderate the panel. Thank you.
Thank you, Dr. Punia, for the kind introductions and for starting this initiative for all of us to join. So moving forward, I want to introduce our panelists and ask them to share their slides. And as Dr. Punia mentioned, please feel free to share your question early on. And we start with some introduction statements from our panelists, and then we will be moving on to your questions and the question that we have ready for them. I'm going to start with Dr. Ahmad Reza Sadeghi. He's a professor at the University of Darmstadt. Dr. Sadeghi, please share your introduction statement.
Okay, just a second. I try to share. So you see something?
Yes.
Okay, so I got some message that I have 10 to 15 minutes time, and I had prepared slides for half an hour. No, I'm just joking. I'm just going through the very short 5 minutes that Swaroop already mentioned to me. So what is my background and journey, and what is the relation to this panel? So my motivation always to do security research was secure distributed computing. And I thought that you can do it with cryptography. This is why I did my PhD in cryptography. And then I recognized that we have much more bigger problems than cryptography, and that are runtime attacks and defenses in software. Afterwards, industry came up with the idea of trusted computing. Then security architectures and enclave computing have emerged. So we looked into that, how we can secure software by using hardware-assisted security. Certainly, this is important for critical infrastructure, where we were very active in attacking them, also together with many partners in the US, and also as a superset, the IoT that emerged from embedded systems. And embedded systems need security as well, because the connectivity aspect and scalability was the new challenge. Now, we always assume that hardware is very hard to attack, or at least we have some trust in our hardware. But we are witnessing since 2017 at least, or let's say even 2014, lots of attacks on hardware. I'm not talking about attacks with nice logos and not really much content. I'm talking about real world attacks that we are kind of witnessing. And if the hardware is attacked as a heart of any computing system, if the software is attacked, then we have a problem with our supply chain. And now there is a big, so to say, trend to AI that is combined with everything. Like it was mentioned that many people work for code generation in hardware and software with AI, and we know that they have vulnerabilities and how we can deal with that problem. That I would like also to mention in this panel, that one day we may not have even IP protection problem because everything is the same, because everybody has access to a large language model and tries to create the code with it. So one thing that I did, started to, set up some startups to have some connection to the real world problems beside the academic research that is not really impactful from my point of view. Disclaimer, this is not the view of TU Darmstadt. But what is the future? I think that our systems should be adaptive, specifically security should be adaptive, that at any time an application says, I want this, and it gets it, so it can reorganize itself, but only the security features. Systems that are reorganizable exist, or at least the idea exists, but I think this is the future that I see for it. With a bit of magic, we may make it. Thank you.
Thank you, Dr. Sadeghi. Our next panelist is Dr. Xiaoyan Yu. She's a program director at National Science Foundation. Dr. Yu, please take over.
Hello, everyone. So I didn't know you want me to talk about the OS program. So I prepared different slides. So maybe because the slides is not supposed to share in the public, maybe I can speak about the changes in the CTC program where I served. So overall, I would say the key message I would deliver is we will have a new solicitation out. It is revised significantly compared to previous program. It's still in the queue. We are not allowed to talk about the details, what has been changed, but definitely it's a bigger change. We call CTC 2.0. It's a new program. We include the new keywords. So please stay tuned. I believe either this month should be okay to be published at the public. So I would say the main change, let me see my slides right here. The main changes, probably you will see it, we will encourage more collaborations between different divisions. That's one key message probably you will see. I think that's also aligned with the topic right here, because when we do more heterogeneous IP integration, we have to be aware of multiple stakeholders, players together. So I will be happy to answer some questions, but I'm not allowed to share some slides in the public at this moment yet. Sorry about that. I thought that you're going to ask me about my own work, so that's a slide here. But I will stay as my OSF head in the Q&A sections, so happy to answer questions, but not share slides at this moment. Thank you.
Thank you, Dr. Gu. Our next speaker is Mr. John Oakley. He's a senior director, is a science director in the Semiconductor Research Corporation, or SRC. Please share your slide and thoughts on the subject as well as your background.
Perfect. All right, can you see that?
Yeah.
Perfect. Well, welcome. My name is John Oakley. I'm a science director at Semiconductor Research Corporation, SRC for short. I have run a lot of the design-related activity and been quite focused on the hardware security, advanced packaging, and AI hardware, which all seems like they're topics of interest today. So quick, I started at Texas A&M many years ago, worked at Motorola, worked on one-way and two-way pagers, mainly worked through cell phones, delivering into the iPhone 7 and 8 and X before I went to SRC. So a quick overview of who I am. But SRC's been around for over 40 years. We have $2.5 billion in research, 16,000 alumni, of which I see some of our professors, and I'm sure we have alumni on the call today. But the goal, as when it was started, is to channel more funds to research and create a quality supply of people, the great researchers that we have. So what do? SRC, we manage academic research projects, so we kind of are a funding agency. We're bringing together semiconductor industry and government together to provide funds and leadership and work directly with the professors. So several professors on the call are work with me and for me. So thank you. But of course, what we get out of it, of course, is most importantly the people. So the students. So our three pillars, I'll go over quickly, are the people, the research scholars. I mean, we've shown that we need a 3x or 4x increase in the number of um, scholars across the industry, but especially in security, in these CAD spaces where I'm seeing a noticeable drop over time in these fields. So getting that interest of the people is one of our biggest challenges going forward. Of course, the planet, there's only one of those. We want to make sure we have green processes and sustainable operations. And of course, what I'll talk more about in a couple of seconds is how do we plan for the future? How do we roadmap? What are the challenges that we see? So just a quick highlight. The ITRS was actually kind of an offshoot of our 10-year goals that we started back in 94 or 84, excuse me. And so this is kind of a timeline of how setting a set of goals, challenges, can then lead to roadmaps that lead and then drive 2D wafer scaling that we've seen over the last 30, 40, 50 years. But as we know, that's slowing down. So we've moved to 3D integration, which gives great opportunities, but also changes the landscape of what security looks like. Once we integrate through other devices, through things, it's getting a lot more complicated. So defining new challenges, new roadmaps. So I'll quickly go over. We set out decadal plan, talking about some grand challenges that we see over the next decade, like the fact that the growth of compute devices like an AI, for example, are growing exponentially. Our world power grows linearly in the next decade or beyond. All of the world's power will be consumed by compute devices. So we need to do something because we want to power our houses and eat food. To that, we then help define a roadmap, the Microelectronics Advanced Packaging Technologies Roadmap, excuse me, of which security is definitely a big topic, along with designs and standards here you see in Chapter 9, and talking about advanced packaging, some of the challenges there. So this roadmap activity was funded by NIST, and the full report is available. You can look at that srcmapped.org at the bottom. And we are working on the next generation of that roadmap, because roadmaps that don't get updated and improved over time get stale and unimportant. So if you are interested, please feel free to contact me and help join the MAP 2.0 team. We are growing that team right now. I think we have over 300 participants defining these various chapters. So mixture of industry, academia, government agencies around the world. So please help us define that future. So that's our plan. Is we started with a what. We talked about how we might do this, and we are implementing the Smart USA Institute. So this is something that we are moving forward with. This is a way that we can grow our academic portfolio by 3 to 5x, which means we're still growing this organization right now. I think we have nearly 200 organizations as part of our Smart USA, and we will grow as this moves into 2025 and beyond. So what's our key focus? I mean, on this is digital twins. But what does that mean? That means that we're actually modeling real world systems, because like, as we talked about, this CAD systems are very complex, these security systems. And once you actually integrate chips together, how do you model this and test this and create let's say properties that you can then map from different levels. How do we actually create test environments? How do we create verification environments? How do we prove that we actually make secure and reliable systems? Very complex, and that's one of the things that we think digital twins will help us solve. So that was pretty quick, but just thank you. Happy to talk more as we get into the questions.
Thank you so much for your presentation. So our next speaker is Professor Farnaz Kushanfar, a leading expert in both hardware and software security. So Dr. Kushanfar, please share your screen.
Are you able to see it? Not yet. It says, Zoom may not be able to record the content of your screen until it is quit. So what shall I do? Shall you have Todd first go and I quit and come back, or I just ignore it and see if you could see my presentation? Let's give it a try. If it doesn't work, we can come back to you. Yeah. So sorry. So can you see it?
Yes.
Yeah, we can. Okay. I mean, as long as you could record it. Hey, thank you for the kind introduction. I guess, most of the colleagues have covered some of the key points that, of course, of the center of the discussion here. So I can't wait for the discussions to start happening. I'm Farnaz. I'm, a faculty in the School of Engineering at UCSD. I'm also the founding co-director of the UCSD Center for Machine Intelligence, Computing, and Security, MIX. And just briefly about me and where my research has led. I have got my master's at UCLA, where I did research on secure physical design, chip watermarking, secure tracing, and combinatorial optimization problems in CAD, as well as invention of methods how you could uniquely trace chips from the supply chain. And when I went to Berkeley for my PhD, I got a master's in statistics and AI with research on massive streaming robust data that was coming from distributed sensors. At the time, I got a nice fellowship from the Intel Labs at Berkeley, so I got to work with the distributed sensor network embedded that was there. And I've worked on real machine learning problems and how you could actually have integrity for those problems, which is what I did for my PhD. So for my PhD, I combined that with making these embedded systems efficient using the machine learning that we got from these embedded systems node. And because I had the background in statistics and machine learning, I ended up getting a job as a DSP faculty at Rice University. So, I, as a Rice faculty in DSP, and Rice DSP group is very well known. For many years, I was actually teaching probability AI courses. At the same time, I kind of went back to some of my roots looking into hardware security, which led to invention of the concept of logic locking and statistical testing, which was not available before, and for which, in terms of doing AI for CAD, I did the first introduction of compressive sensing to chip design and EDA. We were the first to do co-design of algorithm hardware software for matrix multiplication, which was basically what has led to scalable implementation of many of the machine learning models. Also, back when my former student Azalia, who's a faculty at Stanford now, was in my lab, we also worked on the first reinforcement learn-based optimization for power management of chips. So this works have gone back, you know, I guess reinvented themselves. Like, you know, she invented RL-based optimization for CAD later on. And then once I came to UCSD, you know, I now teach computer the engineering courses like FPGA programming, AI, and embedded system security. Of course, you know, all these things have been transformed with like generative models. Like I work on a range of topics in privacy preserving computing, all the way for machine learning for hardware security. And, you know, we all know that AI is enabling a new level of operational productivity. This is cross-cutting across so many different industries. So the vision of the center that I'm running, and, you know, what I will, of course, also focus today is these inventions have been separate. Like, you know, when I was studying statistics or when I was studying computer engineering, all these ideas were separate, disparate in different topics. But really what is really bringing all this together is that we can automate things, and we can use AI tools to automate things, and we can do this automation for security, for hardware, for software, and, you know, obviously for data. And this is all kind of coming together. So really, this has been kind of the vision. So basically, now, obviously, there is a lot of security issues here. Machine learning has a lot of potential, but it also can make error. We can have hardware that can help with this erroneous cases, but also hardware can be impacted. Hardware research can be impacted by kind of AI. And, you know, these are some high-level topics that are relevant to our discussions today. I'll stop here and I'll let, you know, the panel go on. I guess I'm well after my time.
Thank you, Professor Kushanfar. Our next speaker is Professor Todd Austin from the University of Michigan, a renowned expert in the field of hardware security and computer architecture. Professor Austin, please share your screen.
All right, for my Zoom. There it is. You see it? Am I good?
Not yet.
Let's try one more time. Screen sharing has failed to start. The window you selected is invalid. Okay, let's select this one.
Okay, now
Looks good.
Do you see the whole screen?
Yes,
Yeah,
sir.
for presentation.
Fantastic. All right. So thank you for the great introduction and inviting me to be on this. This is a really great resource in the community. Love to hang out with hardware security people. It's always a lot of fun. We're a rarefied bunch. All right. So today I just want to talk about trust. I think one of the great challenges in heterogeneous system design is establishing trust in your hardware. If you're a software security person, you're worried about establishing trust in your software. And then just having thought about this for many years, it is really hard to establish trust in silicon. And I'll tell you the reason why is because it's essentially a verification problem. You have to prove that somebody hasn't done something nasty to your underlying silicon. And that's combined with human deception. So I like to say, establishing trust in hardware is unsat plus magic tricks. And I want to give 3 examples of challenges in trust that I think really sort of illustrate how hard it is to trust hardware, especially when you're bringing in third-party IP and et cetera, et cetera. So Ken Thompson, who was the inventor of C, co-inventor of the C language, when he received his ACM Turing Award, gave a lecture on trusting trust. And in this lecture, he describes a compiler that inserts into itself a Trojan that it then removes from the source code. And so the Trojan lives in the binary of the compiler and reproduces it when the compiler is compiled. Incredibly difficult to find. And it was this that really inspired the work that I worked on, which was the A2 analog Trojan, which was a Trojan that lived beneath the hardware description of the design. It was a 3-transistor backdoor for Linux that you could insert in the fab. And then another one I really love is the dopant Trojan by Wayne Burleson at UMass. This is a Trojan where you manipulate the dopant on one transistor. You can't even see this. You can only chemically detect this Trojan. And you manipulate the dopant on this one transistor, and all of a sudden the random number generator fails. So in my mind, it's not about establishing trust, it's about minimizing trust. How do we minimize trust in these massively heterogeneous systems and really treat trust as a resource? And that really begs the question, is it possible to build computation that can tolerate hardware tampering? And as it turns out, this is actually a very well-developed area of privacy, which is privacy technologies. And I just want to show you 2 simple examples. But first, as a teachable moment, I want to talk about the difference between privacy technologies and security. Privacy technologies are security technologies that give data owners control over their data. So they limit who can see, manipulate, and share the data. And they do this in very special ways. In particular, they limit trust. And pet technologies limit trust across the board: software, hardware, and that's what benefits us, programmers, IT, and attackers. All of those are untrusted. The thing about pets that are really nice as well, unlike much of the work that we do in this community, the hardware security community, is they lean into crypto. In fact, you're not a pet unless you use crypto strength defenses. And when you do that, then you can become, when you build these pets, you're totally agnostic to vulnerabilities. You don't even care about vulnerabilities. And then there's many different kinds of pets, but the kind of pet I just want to talk about today is secure computation pets. Now, what I'm going to show you is not realistic as a solution for how do we reduce trust in systems today, but I want to use it as a method to sort of open your eyes to the possibility that trust is a resource we can spend. And specifically, I'm going to talk about homomorphic encryption, because I always talk about homomorphic encryption. But anyway, homomorphic encryption is a technology it's a security technology that doesn't allow confidentiality be violated. So essentially what it is, it's a way to run a program where the program runs on encrypted data. And so if somebody hacks into the program, they only see encrypted data. But I want to point out, what are the impact of Trojans, tampering, hardware hacking on a homomorphic encryption program? With respect to its threat model, the answer is none. There's no impact on that program. You will never reveal any of the encrypted data through a Trojan or tampering in the hardware. And this is, in essence, a zero trust technology. It's zero trust in the hardware. And so here is a sort of a foothold that we can grab to look at how do we build systems that don't have to trust hardware. Now, of course, there's many problems, really slow, hard to program. But, and what I want to talk about later if I have time, is with just a tiny bit of hardware trust, just the ever so tiny bit of hardware trust, you can improve that dramatically. And this is my work, sequestering encryption. I'm going to jump past this, but with just a tiny bit of hardware trust, you can add a little chiplet to your design. And that chiplet can become the root of trust for the entire design. Anything that chiplet produces will be protected with cryptography. And it could provide lots of resources for safe computation and basically make the rest of the chip just be whatever silicon you want, whatever software you want, whatever design you want, without having to trust all of that. Could do things like, it can be the cryptographic secure root of trust. It can be your on-chip governance, so it can stop your overproduction and turning chips on in countries where it's not allowed. It can provide your secure boot to make sure no one's manipulating your software state. It can do your mission critical computations and check. So I think there's a lot of opportunity to really reduce the amount of trust we need in these future systems. Thank you.
Thank you, Professor Austin. Our last but not least speaker is Sandhya Koteshpura from IBM Research. We're excited to hear her insights.
Thank you so much. I'll try to share the screen here. Okay, thank you so much for inviting me today. My name is Sandhya Koteshpura. I work at IBM as a staff research scientist. I've been working here for the last 6 years, and before that, I did my PhD from University of Minnesota in the area of hardware security research. So I've spent roughly around 5 years in the academic community on this topic, and the last 5 to 6 years in the industry. So I have a good perspective of how the different problems are dealt with in both systems. And coming to the topic of heterogeneous integration or systemic package, the way I tend to think about systemic package is it's kind of a middle ground between two worlds, right? On the one hand, it's an SoC that you are disaggregating into different chiplets and putting them together also. But on the other hand, it's also a system that you are shrinking down, right? The PCB that you are shrinking down and making it into a smaller footprint package. So what SIP inherently does, it inherits the advantages of both system design and SoC design. It gives you a lot of benefits through that. However, SIPs also inherit the challenges of both systems and SoC design, right? So whatever problems you had with respect to security, for example, in terms of IP piracy or reverse engineering, side channels, trojans, right? They're going nowhere. They're still there. There's still huge problems. But also you have this notion of things like component authenticity or integrity in the system that now translates to chiplet authenticity, right? And when you look at the integrity, it's not just the hardware, but you also have to have the firmware. And these things also translate onto the SIP. Other aspects that you have to think about is interoperability, link integrity, or link confidentiality, depending on the threat model, which means that the SIPs need a combination of countermeasures from both worlds. And it was really nice to hear about different zero trust and low trust solutions from Professor Todd. And I totally agree that we have to bring zero trust all the way from systems down to the silicon, right? So it's kind of entered into the silicon world as well. And when I talk about zero trust, I talk about a slightly different aspect of it, which is if you look at like the network security domain, right? That's where this principle of zero trust started, wherein before it was assumed that once you have verified someone into the network, you can just kind of give them access, right? And they are free to go around. And of course, this is a broken model. What we need to do is that even when you are inside the network, you need to continue to keep trusting and not continue to keep verifying and not just blindly trusting. implementing least privilege access, so you only get access to the marketplace you need, and always assuming that there will be breaches and you have to have a way to mitigate those breaches. So these are some of the principles of zero trust that need to come down to the sacred level, right? And if you think about from a systems perspective, since I have worked a lot in the systems area in the last few years, in a system now today, there is a drive to move towards a common security architecture, right? So if you look at this picture here, there is the notion of platform root of trust, which is a central root of trust for the whole system. And this platform root of trust is the one that is talking to a trusted verifier to ensure that this system that it's booting up is in a state of trust, right? And the platform root of trust talks to different components on the system, such as CPUs, your GPUs, accelerators, and so on, to make sure that each of those components are in a state of trust as well. And it's done through various types of roots of trust on that system. And this kind of architecture has to come down to a SIP now, so that every chiplet can be verified to be in a state of integrity, and something like a center of trust, right, that was also shown in the previous talk, can act as that central verifier for that entire SIP. And what I would also like to point out is the role of standards and the open chiplet ecosystem in this kind of bringing this to reality. Because of course you can build all different kinds of countermeasures for this SIP, but when you go to an open chiplet ecosystem where you have different chiplets from different manufacturers and you want to put them onto one single SIP, how do you make all of this work, right? How do you really ensure that my root of trust can indeed talk to other roots of trust chiplet, which is why we need standards. We need these to be baked into the standards. And I work a lot with the standards community as well, specifically the UCRE standard, which is a consortium across different industries to bring these kind of standards very early on into the SIP design, right? And one more aspect is that we have to remember that it's not just important to come up with solutions, but those solutions have to work with the resource constraints of chiplets, right? For example, one aspect is, say you have the central root of trust sitting on one chiplet. How does this central root of trust talk to the other chiplet, right? It seems like a very simple solution, but in order to ensure that the channel between the root of trust and the chiplet is integrity protected, you need to ensure that the standards like UCRE support these protocols from very early on in the stage. And people like me and different industry people are trying to get these kind of standards. So with that, yeah, this is my statement on what are the kind of challenges that I foresee in this space of security for Thank you.
Thank you so much. We'll now move on to the Q&A. Please feel free to drop your questions in the chat.
Yeah. Thank you, all the panelists. I'm going to start with some question and then we will move to the public ones. So we know as the semiconductor industry is confronting the limitation of scaling, heterogeneous integration hasn't emerged as a solution to be able to improve the performance, functionality, and help with the scaling, but it has at the same time introduces new significant security challenges. I want to ask our panelists that as we push the boundary of heterogeneous integration, what do you think are the new issues and vulnerabilities that we have to keep an eye on, and or you foresee to emerge in near future? And how can the research community proactively address these issues?
Is there an order or,
Or random order?
I think random would be the better if you want to share your thought on it.
So shall I start with the random number generator or okay?
Sure,
Shall I
go
start?
ahead.
I
Professor.
can start giving some insights into this if you
So
want.
shall
Yeah,
you start or I start? Okay, you start.
you can start, Ahmed.
Oh God, okay. So, ladies first or okay, so we
Oldest
make it
first.
gender equality says there is no one first, yeah? So I am first. Okay, if you want to know the challenges, we know the challenges already. There is an increased vulnerabilities due to the complexity. Today, everybody wants to have a GPU and a CPU and many other things, peripherals, all kind of fancy stuff, and they don't want to pay for security. This is something that industry is doing in a very nice way, because their risk analysis is based on if there is an attack, what is actually the cost of that attack? Certainly, we think about the security, but as far as we see, none of these architectures, ARM, AMD, Intel, doesn't matter. So I'm in business with Intel in the last 15 years. I see that they certainly take care of security. They take it very seriously. But we see that due to the building on the legacy SoC, the attacks are not stopping. I mean, real world attacks. I'm not talking about some microarchitectural attacks. I'm talking about attacks that you see in the wild and can be very expensive. And the scenario that I personally really like is the Armageddon scenario, because academic research, as I said before, in this area, there are many nice papers, but none of them has really an impact because none of them is really applied. We have the technology to make the current hardware more secure. I say more secure, and we have to define what are the requirements. But I think that there is no transformation. We need a transformation because we have to go away from old systems. One day, when everything is with AI equipped, let's say, assume this dystopian world, AI is everywhere. AI is a gold mine for security. And then connectivity comes to it. Then we have a scalable, connected malware or attacks if we have one or more comprehensive, sophisticated, so to say, vulnerability in the hardware. We have seen it in the last 2000, from 2018 to now. We have each year at DAC, one of the world's largest security competition for hardware, where Intel and Synopsys are our partner. And we see mind-blowing and eye-opening attacks to the hardware, real-world attack that can compromise systems in a large scale. So with current approach, I don't see any hope that we sit here and talk about security.
Great. Dr. Kushanfar, can you share your thought on it? Oh, you're mute.
I said it's hard to come after Ahmed. He has a lot of insights and great opinions. But I really think that, as Ahmed said, of course, automation is the key, as I was even showing in my slide earlier. But I think, a major hurdle in particular that arises in heterogeneous integration is a classic thing that happens all the time in system security, and that is that usually we're not very bad in securing components, but when it comes to interfaces and when things get connected and communications, that's where a lot of vulnerabilities come in. So there is a lot of opportunities with this heterogeneous integration for cross-domain attack. Of course, some old ideas like isolation and bootstrapping trust could help from one domain to next, like, some of the work that Ahmed has been doing on bootstrapping trust for higher level systems or others. Definitely with this interfaces coming into the game, there's an increased attack surface. And of course, again, we have to have a way to maybe formally verify or audit and monitor these interfaces to see how they're doing and how they're behaving, to try to somehow have a control over this increased attack surface. Obviously, the heterogeneous integration, you have a lot of IPs. There is a chance for poisoning, Trojans to get in. And for that, again, we have been working on these problems for many years, but they're constantly changing face. And, the interfaces and secure interfaces have to be developed and formally verified. And of course, last but not least, an area with heterogeneous integration that has caused a lot of issues, for example, with the attacks we have seen in the last 10 years with Spectra and Meltdown and all that, is really the interface between hardware and software. How you could have that also taken into account. And of course, AI provides a set of great tools for this, but AI agents also have to learn. And a huge question is, where do you start learning and where do you get all the data? And you have to have a structure for learning all these. And these are so many different problems. So even though at a high level, you could imagine that automation is a key and can be done, I don't see an easy way to do it immediately, say in the next 1 year. But so these are some long-term research questions that we have to deal with.
Thank you.
I'll jump in if that's okay.
Sure.
So if I think ahead like 5 years, design is going to be with chiplets. Chiplets are going to come from third parties almost always. You may not even design a chip when you build a hardware system. So you're going to have high integration, high third-party integration for a lot of, I hope, for a lot of designs, huge complexity. And so with the huge complexity comes many, many vulnerabilities and side channels. So I think the key takeaway from heterogeneous design is that if you're trying to fix vulnerabilities or mitigate them, the arms race in the hardware world, the security arms race is going. It's now moving. And so you can be a part of that until the end of time. Also with third parties, there's the supply chain attack issue where someone could put into your design a backdoor that you may not be aware of. And I think the other big challenge, and one that I've really experienced in my non-academic side of the world, is cost sensitivity. There's really a high insensitivity to the cost of security technologies in industry. And I think we've seen examples of, companies spending money on security, but then they tend to dial that back pretty quickly because I don't think we're producing technologies that can really provide a good return on investment. And in that regard, I would just say that while security doesn't sell, privacy does sell. So if you can build security technologies that can be used as privacy tools, so the difference being security stops hacking, privacy basically builds a wall between sensitive data and the system that's operating on it. I think if you build privacy technologies, it's easier to make that case from a cost perspective. And I hope that the world will embrace those kind of technologies. Otherwise, we're just going to be forever in the arms loop. Thank you.
Yeah, maybe I'll say something. I mean, it's a great question. I think as we look at the future of 3D integration tools, heterogeneous integration, we're going to have tools that are going to, as you said, look at software, hardware, look at chiplets, and build effectively heterogeneous systems. Some you may have, some you may not. You're going to have through silicon vias, through devices, which actually opens up a whole new game because it's not difficult to measure current going through those things from the chip that is the one that's the interface. If you're all integrated in one chip, then you can see if someone put a monitor there. But when you have these heterogeneous systems, it's hard to see these monitors or even detect that they exist. All you can see is a little bit of energy loss maybe, and that's resistance, which could just be a byeffect of having a through TSV or something. But I think the tools are going to start creating chips for you, creating designs for you. They can add stuff to those. I think AI is going to be a great support for our industry, and I think we're adopting that across the industry now, these AI tools, but it's also a great hindrance because people trust things because they don't test it well enough, right? So testing becomes a big problem. How do you prove that this is still good? How do you detect that someone put a defect? The needle in the haystack problem, right? We are creating super giant haystacks that we've never seen before, and putting a little needle in there is it's becoming easier as time goes on, and I see that to be the biggest problem. So how do you secure things through these interfaces? I think it's going to be a challenge.
Follow up the previous panelist comments. Those are great points. So indeed, like when we do heterogeneous integration, we actually have more dimension concerns, right? If not only two-dimensional, maybe 3Ds or kind of connection. So those integration technology will bring in new threats. Some already being investigated, some have not. So one concern I have is when you integrate all those IPs in a way that how much information should we share between the IP providers, right? It will be better we have more transparent information to share between so that we know what has to be public, what is not. But on the other hand, for system designer, you want to get more information to design better verification plan, knowing that what can be tested, what cannot. Maybe the community can think about how can we create like a standardized protocol or policy require IP providers what should be shared, especially for industry, consider the cost. They should say, okay, hey, this policy or standards already be accepted for the entire community, please, let's follow that way. In that way, we can mitigate like the cost concerns, like, oh, I don't want to leak info, because everybody have to follow the same way, share same amount of information for good amount of interest required by the community. So I think that probably help us to address some of the IP privacy issues, but also help the integration, because this is the standard everybody has to follow. If you want to get into the market, this is what we required. So community can build this kind of pressure to the industry in a way that they cannot get away from it. So I hope that this will be helpful for us to push the heterogeneous integration.
Yeah, and I would like to add to that I think the biggest challenge, as I mentioned, towards bringing this kind of heterogeneous integration to reality is making security that works for all chiplets, right? Whatever be the type of chiplet, whatever resource constraint, whoever is manufacturing it, have standardized security modules that work on all and that work together with each other. So this has to happen very early on. It cannot be done later, right? Like you build the chiplets and then try to stuff in some security. It's not going to work. It has to be there as the chiplet ecosystem.
Thank you, all the panelists. So we move on to the next questions. We know that the AI is the hot topic. It's been for quite some time. And we actually have a question regarding the new generation, the large language models. So the question is, how do you see the role of these large language models evolving in the hardware security field? And do you believe their popularity and their relevance will continue to grow in the coming years? Can be actually LLM help with the heterogeneous integration. I know Dr. Sadeghi mentioned maybe that would be the solution, that we don't need IP security even in the future.
I mean, I'll step in first. I think these large language models are growing. They will be used. So they're becoming mainstay now. I mean, people are using ChatGPT. They have Copilot in their phones. They have it's integrated into all tools, and will continue to be integrated. It has great benefits, but also it abstracts things away. So we're going to have experts like you guys that are going to be experts in the field, but everyone else will be pushed away and not even think about security. So if you can't teach these LLMs to be secure, somehow make it secure, you're losing expertise or even awareness probably in the greater audience, because they assume the tools will save it for the do it for them. As we see now, I mean, not many people can read a map anymore. They expect their phone to GPS for them, right? LLM will do the same for a lot of things. I don't know. I consider it to be a great tool, but also it's going to separate the experts from the generalist, and the vast populace will be just generalist, and they won't even think about it.
You can say the same about the attack side as well,
Of course.
right? In the world of attacks, they call you're either an expert or you're a script kiddie, as they call you. And,
Yep.
and what LLMs will do is they'll allow the script kiddies to be much more productive and to basically find their own zero-day attacks. I think it'll be really interesting to see if LLMs can find new attacks. Can they find new classes of attacks? To me, that would be the highest form of LLM, because it really the amount of ingenuity and human cleverness required to find new classes of attacks is very, very high.
So we raise hand or we just jump in?
Jump in.
Okay. So I don't know if anybody from audience has or participants has any question, but I mean, this is an interesting point. Using LLM. So what are the advantages? The advantages is certainly if you use, this is what we have been doing in the last, let's say 2-3 years, understanding if LLMs can be used to find hardware vulnerabilities, new vulnerabilities. What does it mean, new vulnerabilities? Do we have access to the to the CPU design of Intel or NVIDIA or GPU design of NVIDIA? We don't have. So the only thing that we can do is we take open source platforms and find new vulnerabilities. But what is actually the interesting part of LLMs for hardware security is the interconnection between the instructions. If you do any test, even if you use formal methods, due to the scalability, an LLM, if you consider the instructions and assembly language as the language of the CPU or any other hardware, and then you consider LLM as the one that analyzes the instance, the entity that analyzes this language, so you can find interconnection between instructions that can lead to an attack window. Yeah, so this is something that we have observed, and we think that this works. If it works, and if it works for a, so to say, very complex SoC, we don't have anything else. If you use formal methods, it will fail because it has state explosion and many other problems. If you use fuzzing, it is faster, it is cooler, but it has still also its own saturation problems. This is also something that we have been working on a lot to understand if fuzzing could give us better results in finding vulnerabilities. This is the positive part, but what is the negative part? I love when organizations use Copilot and or other language models for creating code. Todd mentioned script kiddies. No, these are really developers, because they can fire some developers and keep the most experienced one and say, okay, you look into the code that Copilot generated, but this will have, due to the complexity of heterogeneous system, will have consequences. which actually I love. I really encourage companies to use Copilot because we will have 20 more ideas for PhDs and many, many other papers for conferences. From academic point of view, that is a great, great gold mine. But from the point of view of system design, certainly this is a tool, and one day, like a compiler, LLMs will be also another tool that you use for improving something in your code. But the scalability and the non-explainability of what is code, why this code does this and that, without further checks, that is mostly by human. And if you want to have another automaton that checks the output of the LLM for a code, you need to use static analysis, you need to all the tools that we already know. So it's not going to reduce the work. It may ease the work for in certain cases, but also for security that will have in certain cases, to my view, to our experience, fatal consequences, which we like actually. We like Armageddon, as I said at the beginning. Armageddon is very good for security researchers.
I want to echo Ahmad's comments. Say the AI tools actually will ease the work as a team effort. Because when we say heterogeneous integration, that means we have different experts in the same team. They do not necessarily understand each one's concern. The high-level tools can help us to understand what is ultimate goal as a team and translate it, for example, a verification plan or some security examining strategy plan, right? So have different levels of concerns they can put in a team effort. And then we can go one by one as a single teams. Other things I would say, high-level language really can help us to say, okay, they can search basically, right? Search each vendor's the key features or specifications. They can translate it to what we need in our verification stage. So using these tools, it can help us save times to memorize, what should we look, what should we let it go. So I think the high-level tools can ease the teamwork for sure, but as for domain knowledge needed tools, then we can divide with small pieces and conquer for each small groups. So I think this is how high-level tools can help us for team measurement perspective.
And I think LLMs can help with the scalability aspects, right? So supposing in future we end up with like 100 chiplets on a chip, and just imagine that. But if you have that kind of level of different triplets all sitting in one package, and you need to do a risk assessment of this whole package, right? How do you identify the different assets of that of the different chiplets, right, coming from different vendors? So large language models could help with that kind of information. AI in general could help with looking at the large amount of information flowing in and out of the triplets and making sense of the entire information flow for that entire SIP, right? So these kind of scalability challenges, I think, will need some level of both automation and AI to help us.
Dr. Austin, I see you have.
I just have a semi-cheeky follow-up. If you work in defenses, you can probably rely on the fact that cryptography will not be broken by AI, because cryptography is based on mathematical formulations that humans do not know how to solve. If AI does break your cryptography, it's time to move off the grid.
Any last thought to share?
So one thing that I mean, I agree that cryptography is based on unproven mathematical assumptions, and we don't have algorithms currently to break them, at least when you consider the key length of RSA or in the public key scenario and in the symmetric key setting, which is a kind of standard things, the standard cryptography that we use. However, if you consider the academic research in the area of accelerating side channel attacks to extract the keys out of the processor due to many other problems that our processors or hardware in general has, and that is information leakage. And that is exactly the problem of sharing resources in your system, whether it's cache or certain buffers or certain registers that keep the values, they do not evict it or they do not delete it. But if you consider how many papers now is published at Chess and I don't know, Usenix or whatever, that just try to extract the key by accelerating side channel attacks using, so to say, deep neural networks, then we have a problem there, at least from academic point of view. From industry point of view, we don't hear much except when academia attack a real world chip and then present it in black hat. So I don't think that cryptography is a help, kind of supportive for whatever we want to do, if it is IP protection or if it is isolation. If you have enclave computing, you need cryptography, you need integrity checking. But in general, as long as our systems are designed as they are designed now, you will have other problem, cover channel, you will have side channels, you will have many other problems that also bypass the cryptography, not only break it, but also bypass the cryptography.
It's a quick follow-up. So I would argue that cryptography is the only durable form of isolation, right? Air gapping, not durable. Cache partitioning, not durable. Anything with a shared clock or power line, not durable. That cryptography really is the only thing that is a durable form of isolation. So and all the problems you were mentioning there, I was saying, oh, should encrypt that, should encrypt that, should encrypt that. In fact, I see a Spectre paper, I say to myself, they should have encrypted that.
No, but I mean,
But
yeah.
I mean, Todd, there is an overhead with encryption. So, I mean, I work on, the domain of cryptographically based secure computing for many years. And, there has been some great progress in implementation. But at the end of the day, there's always the overhead is, of course, not manageable for all applications. But, when you look into encrypted, at the end of the day, who has the keys? So if you're talking about trusted platform, there is a key that physically is stored there, and if it's a distributed system or distributed management system, there's there is a key management that becomes a hell. It's not just there's this key, but how you manage the keys, who has access, how you store the keys, those things actually are becoming more roots of vulnerability than just the crypto algorithm itself. Of course, crypto is beautiful, and if it solved all the problems in the world, we would not be standing here having this panel, right? So, I think there's a lot of challenges. I don't think, this is just an easy fix, which is good for us because we will have many years of research and development to overcome those. So, I guess, we need NSF and SRC to support our research.
Yes, SRC.
I would just point out Lauren Bernanke, who just graduated from University of Michigan. She worked on the sequestered encryption work. She showed using, side channel free caching that she could do 100% encrypted computation within 15% of native. And the keys are protected. They're just encrypted in memory. So, I think their solutions are emerging. And if we want that, what's really great about sort of end-to-end verify, I had a paper that did end-to-end verification on that as well, formally. The great thing about these end-to-end verified cryptographically secured hardware systems is they can be used to solve privacy problems too, which is really a value added for a system.
Maybe just in one
from audience.
What?
So we have a lot of questions from the audience. And limited time, I would appreciate if we can next to the next question. Banafsha?
Hey, Rosie,
So
just to let you know that there are some questions in the chat window also. So Q&A has 7 questions right now, and chat window has probably
So
2
we
or
go
3.
first with Q&A and then for chat or what?
yeah, let's go with the Q&A and we
Yeah.
quick go over. So the first question is directed to Dr. Sadeghi. Considering your impactful experience beyond the academic setting, how does the integration of analog and RF components affect IP security differently compared to purely digital systems?
Oh, wow. So there is, of course, okay, I cannot really answer this question in a detailed manner because I'm not any expert in analog systems. But there is, of course, a movement with analog systems, not for security, mostly for efficiency. And certainly, if there is a pure analog system, it has some advantages regarding security. But if they are combined with a digital system, then you open again different attack surfaces. Either it is information leakage, or it is a combination of components that they are interacting with each other. And there is another aspect as well. So if you have RF and if you have analog system and you want to have an analog cryptography there, and on the other hand, the digital system that is connected to it has digital cryptography, so to say. I just focus on cryptography because I think I know that Todd likes cryptography, but I think the biggest problem, as Final said, is the key. You can encrypt the key at some place. You will decrypt the key to use it, unless you use fully homomorphic encryption. And until fully homomorphic encryption has multiplied 2 bits, you can go for shopping, have a shower, come back, sell your car, and still it is multiplying. So that means there is no real efficiency. So now think about this system with analog and digital. How it works, I cannot tell you, but I can say that analog has its problems with security. In some cases, analog systems are more, so to say, more safe. I would say safe. I'm not saying secure, because security, you need to know what is the requirement. But both systems have side channels, both systems have radiation, both systems are vulnerable to certain attacks. So I don't know if the combination is very hard to secure. We have RF security, we have this is why, for example, in the area of 5G and others, we still have problems because of some combination of analog system and digital systems. That is as far as I can answer you. But maybe you send me the question in more details and I can look into it with my team.
Sure. Thank you. So the next question that we
Wait,
have.
can I make 2 quick points on that?
Sure.
One, Ahmad, you can decrypt the key, you just can't let software touch it. Then you don't have to be homomorphic encryption. Okay, and then the second point is analog systems, while they may be more secure, huge privacy problems, right? Because analog systems reveal process variation in how they compute. And so there's been lots of studies that have shown that analog systems, you can tell what piece of silicon produced an analog result. And so that I think that's another.
No, you have side channel. You have definitely.
You lose one thing and you gain another problem.
But if you don't want to access the key, just going back to you need trusted hardware. There is no other.
Oh, you got to have some trusted hardware. I agree with that. But you just have to trust. You only got to. You only have to trust the thing that deals with the key and the crypto. You don't have to trust the DRAM that you got from a third-party vendor that's sitting, 3 hops away on your CXL bus. So it's a good root of trust capability.
Yeah. I mean, if I have the assumption of root of trust, then we are in business. I don't care about cryptography. I have root of trust. So I mean, I assume that my key is supported, even if it is encrypted. Doesn't matter. It is supported by root of trust. If there is no root of trust, no this assumption, I don't know how we can do it. Yeah, of course, that's maybe there are some more exotic methods to use to keep the key secure, but like you can have puffs or whatever, but all these things have been shown to be either breakable or, as I said, we need to rethink about a transformation from our systems today to a kind of more flexible systems that you even can patch it post fabrication. That is what I would love to see people do more research in for the security aspects, only for the security aspects.
Hey, it's such a stimulating discussion. We have 9 questions and 9 minutes. So maybe each question one of the panelists can answer, maybe in 30 seconds to 1 minute. Rosine, please go ahead.
That would be more helpful. So the next question is, how do you see the existing security solution like logic locking play out in the context of heterogeneous integration?
I'll take a quick one. I know we funded a lot of research in this realm, and I think we can mathematically prove, and it's been done a few times, that most logic locking or all logic locking systems will be broken given enough time. I think there are other solutions that we can use beyond logic locking personally, but I know that people are still working on it, so we haven't at least maybe found all of the things, but all the existing ones have been broken relatively quickly. So I think there are going to be other solutions beyond logic locking.
Thank you. So the next question talking about, we have seen progress in photonic-based hardware accelerators as the transistor size in silicon approaches its limit. The industry has been shifting toward the photonic and other emerging technologies. How do you think it affects the hardware security in the context of heterogeneous integration?
All right, I guess I also fund research in basically photonic AI accelerators. I would say AI, photonics, AI math, or photonic math, and that work is still in its infancy, is very temperature dependent today, is very process dependent, and it's I think we have a ways to go before we're really going to be integrating this into a, let's say, a computation. Right now, on the communication side and maybe a modulation side, I think we are better at today and will be improved. But there are some initial work on how we might use AI for AI accelerators. I think that's going to be like step one, but there's some, let's say, probabilistic errors in there that occur, but just because of the nature of heat, process, uh, angle of impact, and things like that. So it's going to be interesting. I think photonics still is a work in progress, personally.
Thank you. There has been a couple of questions about the interface between chiplets. There's a question about, is works being done enough in the UCIe security development area, as well as the other interfaces, and how we can detect anomalous behavior and secure these communications.
Secure what? This communication.
The interface between the chiplets, such as UCIe.
Yeah, I can answer a bit to that. So I do work in the CI consortium. I'm in the security and manageability work stream. So that's our primary goal, to make sure that we have security, as I said, included from the very beginning, right? So as the management spec is being drafted, we are adding in provisions for security. This includes very, very early things like how do you load firmware, right, into a SIP. So how do you do that? You have provisions where you can verify that firmware. You have provisions where the root of the primary trust can verify things, verify authenticity, for example, of the chiplets before it sends the firmware to that chiplet. Can it collect measurements from the chiplet so that the entire SIP can be attested before that SIP is properly let into a larger system, right? Things like that. We're looking at it and the interface between chiplets. So UCIe primarily looks at like defining the physical and the link layer of the connection between chiplets. What we would do is to add things like integrity protection into the packets, so when they are traveled, right? So things like that. So we are definitely looking at those aspects, and as I said, looking to make it work such that regardless of the industry, regardless of the type of chiplet, it will work, right? So because in our consortium, we have representation from automotive, IoT kind of domains, or processors, and all the different type of SIPs that we may see.
Thank you, Dr. Kudeshwara. The next question is, will we ever see an entire chiplet design around attacking system in package? And if so, is it realistic to be made in a nation state level, or should it be done more in the academic level at lower abstraction?
Okay. I did not completely understand the question with one nation state.
This is a
So,
question that as well in the chat.
okay, in chat, so I didn't see that question. Okay. I don't know what is about the nation state. Certainly, given the current geopolitical tensions, we are going to this direction again, that governments do not trust others or companies outside their country to create chips. I mean, if it is about building secure chips, certainly we are going to this direction with CHIPS Act and many other active political initiatives in this reason. But this is more politics. And I don't think that academia will, they will play an important role as a kind of, okay, we have shown the feasibility of this thing. But the question is, would industry jump on it and take the solutions from academia? It's usually my experience, certainly others have other experiences, is that it takes a long time that companies would take your solution unless somebody convinces them, hey, take the solution, it's very good, and pay them money. And sometimes you see that many ideas of academic papers, they are building in products without even acknowledging the academia. This is not only in US, but also in Europe. You see that the big companies do that, and we know that. We don't just talk about it. So now it's panel, we can talk about it. So I think nation state, when it comes to building secure systems, we are going to this direction. When it comes to attacking systems, we are going even faster to this direction. That nation states look at the pager attacks, which is a very simple compromise of supply chain that kill people, doesn't matter who, kill people. And whoever is dumb enough to do that, it opens the door for others to do that. Next, you buy a washing machine, and maybe there is an explosive in it. And somebody will send a kill signal to it. So we need to think about this Armageddon scenarios, yeah, and that's what will come if nation state touch on it, because they have all the resources.
I think if you look at like ARM's vision of chiplets, for example, not NVIDIA's vision. So NVIDIA's vision of chiplets is how big of a chip can I make? But ARM's vision of chiplets is more like an ecosystem where I put together my system, I get this chip, that chip, and the other chip. And I think in that world, you don't need a nation state to do a supply chain attack. You can just, have a bad apple on your design team, and you can basically put in an attack. I think the key to dealing with this problem is that UCIe and CXL and other bus standards have to really sort of take a zero trust approach for how things live on the bus. And you always have to assume that somebody on your bus is evil.
I want to emphasize one program ISF is pushing right now. It's called the RINGS 2.0. This is a program promote the collaborations between academia and industry partnership, so they can contribute. Ring have the first version, it was very successful. Now we push into the 2.0, try to encourage the community to use existing Ring facilities available and bring in more industry people to contribute, building a collaborative project between ISF and the industry. That's going to promote like some implementation like chips very well.
John, thank you for the information. Can you put the link to this program in the chat?
Let me search. Okay. No.
Great question.
And
Um,
so Last question, Banafshe, go ahead.
There's a question for Dr. Kushankar, and the question is, what are the security challenges for now in using AI accelerators in federated learning when dealing with data or corrupted model updates?
So I guess that's a complex question, but the federated learning, I think when people say federated learning, very often they refer to the Google notion of federated learning, which is privacy preserving federated learning. And I'm assuming that's like what the question is asking, because once you have a privacy preserving federated learning, the problem is data poisoning becomes a real issue. Because if you're doing all the accumulation in private, then how do you know that these accumulations that are done in private, somebody doesn't inject a poisonous data? And that's a really nefarious attack, which we would not be able to address in the context of the present federated learning setup. We have been actively actually working on some of the solutions to this problem, and the solutions are based on adding crypto. Obviously, adding crypto provides strong guarantees, but at the same time also increases the overhead. So there is definitely that trade-off. For example, we had a work based on using zero-knowledge proofs to prove that things are not poisoned before you could integrate that in the privacy-preserving learning. And the big problem with that, and that's why we're actually working with some really world-famous cryptographers on this, is how do you actually do these robust statistics with crypto in a scalable way? Those are some of the open problems in cryptography, which I believe if addressed, and of course in a lightweight, like my hat as a computer engineer is always how you make things scalable and practicable. And that's like, I think, some of the problems that are on the forefront of crypto and security or system security, as if you think of federated learning as a method to and as a system method. So it's really not a hardware method. It's more of a system method to integrate a lot of learning scenarios together.
Thank you. I would like to invite Professor Gang Gu to deliver today's closing statement for the panel.
It's Gang Q.
Oh, thank you.
Hey, Professor Gankyu, you're muted.
Yes.
I'm sorry. I'm Gang Q, and somebody correct the typo there is QU. And I'm a professor at the University of Maryland. And more importantly, I'm the co-founder of this hardware security and trust technical committee, and which is sponsoring this online seminar series. So first of all, I thank all the audience who are from all over the world to attend this, very, very informative, very, very helpful seminar here. It's on very, very timely topic. And second, I would like to thank all of my friends who are on the panelists, Farnas, Chao Yan, Amar, Toad, John, and Cynthia. And it's great. Since you guys can take this 1.5 hour plus from your busy schedule to give this very, very, your shares about your thinking of this very important topic. And I would also like to thank, the two, moderators, Rosine and I don't know how to pronounce your name. So Banafasha, and for you to help, moderating this session. And also the man who is behind this whole thing, Professor Shruv Banya from University of Florida, who started this initiative. And finally, I want to thank, Laura from CEDA, so who is providing a lot of help, sending out announcement and then trying to get Zoom all these things set up. I think it's pretty late for some folks in some part of the world. So thank you again. I mean, the panelists very, very much. And hopefully we're looking forward for the next seminar. Thank you.
Thank you. Bye.
Thank you, everyone.
Thank you.
Bye-bye.
Thank you for the invitation. Bye-bye.
Thank you. Bye-bye.